And what we're going to talk about today is angular momentum. And angular momentum is like linear momentum in much the same way that angular kinematics and angular dynamics were like linear kinematics and linear dynamics. There's sort of analogous equations. We have these quantities that are angular quantities, and if we put them together the same way that we put together the linear quantities, we get angular equations for kinematics, Newton's second law, and momentum. So the goal for today is for you to be able, the big goal is for you to just be able to talk about this stuff. Ideally, we would be able to communicate about angular momentum and its relationship to angular velocity and moment of inertia. Much of what you're going to work on today has to do with moment of inertia. Moment of inertia is the trickiest concept when it comes to angular motion. It just doesn't make sense to us. I think a lot of it just has to do with the name, unfortunately. And then the work that you do later in the class period is going to involve making measurements, analyzing your measurements, trying to make predictions. And it's not going to be a perfect, we're not going to get data that's as good as what I like to have you get, but it'll do the trick and it'll give you the opportunity to kind of play around with some fun stuff. So angular momentum is like linear momentum in that it involves both the resistance of an object to changes in its motion, which we call inertia, and in linear system, the measurement of inertia is mass. Mass tells you an object's inertia. It's resistance to changes in motion. And in rotating systems, inertia is what we call moment of inertia, which is a weird term that I prefer to use rotational mass or angular mass in place of. And that is an object's resistance to change in angular motion. And then it's also related to velocity. Velocity is how fast something is going. In linear systems, we measure velocity in meters per second. In angular systems, velocity is measured in radians per second. And the equation for angular momentum is analogous to our equation for linear momentum. Angular momentum, why do we use a capital L? Anybody know? Come on, you guys should know this. You don't know this? Jack, how do you spell the word angular?
A-N-G.
Uh-huh.
U-L.
Wait, you what?
U-L.
Capital L, thank you. U, capital L-A-R. That's how everybody writes the word angular. We can all agree on that, right?
Yeah.
So, and that's why we use a capital L for angular momentum. And that's going to be equal to I, moment of inertia, times omega, angular velocity. And we'll go into this a little bit more in a second, but that is analogous to our linear momentum equation, which is linear momentum is equal to mass times velocity. What does that mean? It means that we are looking at an analogous conceptual quantity here. When we were looking at linear momentum, what I told you is that tells you how hard it is to stop a moving object. What determines how hard something is to stop? How much mass it has. More massive things are harder to stop. And how fast it's going. Things that are moving quickly are harder to stop. Angular momentum tells us how difficult it is to stop a rotating object. If it's rotating, the speed of rotation will change, whether it's more or less difficult to stop, but also its rotational mass will change, whether it's more or less difficult to stop. Imagine that you had a little concentric pulley like this one. It's spinning around. You want to stop it. That's pretty easy. You just put your hand on it and stop it. Now imagine that you had this bike tire. Sorry. And this bike tire is spinning around. Would anybody want to stop this? I think you could stop this with your face. Right? It's not that big of a deal, right? But if it's going really fast, do you want to stop it with your face? I wouldn't now, because I could feel those other two, and I think this would burn. If I wanted to stop this, I wouldn't even use my hand. I would like I could feel the heat just from that, right, through my sweatshirt. So the speed with which something is moving affects how difficult it is to stop its rotational motion, but moment of inertia does as well. So I'm gonna ask for a little bit of assistance here. I'm not gonna, this isn't gonna be like a hurdy thing. Okay, what I want you to do is I want you to stop this from spinning as it comes towards you. Ready? Go. Hang on. Okay, got it? And now I want you to stop this as it comes towards you. Okay, ready? Did you feel the difference?
Yeah.
Which one was harder?
Blue.
Yeah, it's a little bit more difficult to stop the blue tube because it has a higher moment of inertia. But they have the same mass. One of the things that I want you all to do today as part of your exploration of this is make sure that you know that these two things feel the same if you move them around in a linear way. And you have to be careful, because if you're moving something around in a linear way but you're wobbling it, then you'll feel the difference. But if you keep their orientation in space and shift only their linear position, they will feel exactly the same. Their resistance to changes in motion are exactly the same. If you gave me these two tubes and my eyes were blindfolded or closed and told me to pick them straight up like this and asked me which one is which, I would not be able to answer that. They feel exactly the same to me. And we actually tried this in the first period class. There was a student who was like, I can tell the difference. No, he couldn't. He was wrong. We got him. It took 2 tries, right? The first try he was like, this is the blue one. The second try he's like, this is the blue one. No, you can't. They're the same mass. And as soon as you twist them, you can feel the difference. It's so much easier to change the spin of the red one than the blue one. The blue one and the red one have the same mass. The blue one has a greater moment of inertia. You get more moment of inertia. You increase moment of inertia by either making something heavier. That's not the case with these plastic bars. They have the same weight, they have the same mass. Or by distributing the mass differently. If mass is far away from the center of rotation, it's harder to get it to spin differently. If mass is closer to the center of rotation, it's easier. And so when we look at angular momentum, and we'll look at this in just a second, it's increased by either increasing the angular velocity. So objects rotating with a larger angular velocity will have more angular momentum, or by manipulating the mass, which we can do in a couple ways. So objects with a greater moment of inertia will have more angular momentum, but we can get a greater moment of inertia by either adding mass to something, and we can do that. It's not super easy though. When we were dealing with linear momentum and objects that were colliding, one of the things that we noticed is that pretty much the masses always stay the same. Like, we didn't even need to think about it. We have 2 objects, mass 1, mass 2. They're always the same. With rotating objects, it's the same thing. Like typically, when you spin something, its mass doesn't change. Like, we're not going to see this concentric pulley change mass as it spins. Now, could we figure out a way to do it? Yeah, I'll show you a way to do it in just a second. That's not too challenging. We actually have a similar way of dealing with linear objects as well. But what we have with spinning objects, rotating objects, that's really different is that we can affect moment of inertia by redistributing existing mass. And that we can do in 2 ways. One way is with machines. So if you have like a bar like this and it's spinning around in a circle and you have a mass on that bar, but the location of that mass is determined by like a little motor with gears and pulleys and stuff, then you could move a mass farther away or closer to the center of rotation easily. It's far easier to do this with biological systems though. Okay, so let's try it. Ready? I need a volunteer who did not eat too much for lunch. Don't all? Just kidding. I'm gonna pick on somebody. I don't really care. The 2 most likely outcomes of this involve puking and concussions. So who should I pick? I think Finn. Finn. Yeah. But don't worry, there's plenty of horrible experiences to share. Okay, so Finn, hop up here. Okay, and then take these bars and hold them right up close to you like this. Okay, and then when I'm going to have you move them out in a second. You're going to have to move them out and up because otherwise they'll bump into the table. Okay, so I'm going to spin you a little bit. Okay, do you feel like you're going too fast?
No.
Okay, take the bars, move them out. Feel the difference?
Yeah.
You guys see the difference? Now move them back in. You see the difference again? It's a little bit less, but every time he moves the bars out, thank you, he slows down. And that's because his moment of inertia has increased. But angular momentum is a conserved quantity, just like linear momentum, which means that unless there's some external torque on an object, its angular momentum should stay the same. There's a couple things to think about here. The simple things, which is what we're going to look at, are things like what you just saw. When you have an object with a changeable moment of inertia, its angular velocity will have to change as its moment of inertia changes. Angular momentum has to stay the same. So if L is constant, and it's equal to moment of inertia times angular momentum, then increasing moment of inertia means that we have to decrease angular velocity. And that happens. And it's actual forces that do that, right? And the details are way beyond what we're going to look at here. But it does involve actual forces. There's more to it. You'll see some examples in just a second, but there's a couple more pieces to this. One has to do with subatomic particles. Anybody here who's done any investigation into modern physics, particle physics, has anybody looked into that because you're a dork like me? Anyone? No, that's fine. So basically, there are all sorts of little particles, things like quarks and leptons, and all these things have a quantity associated with them called spin. And we don't really know if they're moving or not, but that spin reflects angular momentum. So particles that are smaller than atoms, smaller than protons, neutrons, have some sort of spinning quality that is essentially telling us about the angular momentum of these particles. And literally the very fundamental physics of our universe is in part governed by conservation of angular momentum with these tiny subatomic particles that we don't even really know what they are. So we get all sorts of really cool things with particle physics. Like, has anybody ever heard of quantum entanglement? Quantum entanglement is the idea that if you create two particles at the same time from nothing, which already sounds insane, but it can happen, two particles can spontaneously spring into existence. Because of conservation of angular momentum, they have to have spin in opposite directions. So if one has one type of spin, the other will have to have the opposite type of spin because there was nothing there to begin with. So you can't have a creation of angular momentum out of nothing, so it has to be equal and opposite. But if those two particles are created under conditions that cause them to separate rapidly, it turns out that measuring the spin, so the spin is indeterminate at first. Like, we don't know what it is, and it could be either, it exists as a probability, but it turns out that as soon as we measure the spin in one of those particles, the other spin is also determined. We don't really know how this works, and it would work at any distance. So potentially, there could be two particles in this universe that are of indeterminate spin that have to be opposite, but their current spin, their current angular momentum is basically a probability wave, but as soon as we make a measurement of one of them, the other one gets locked into place. And we're not quite sure how that works because it doesn't seem possible, but then again, none of this stuff seems possible. I don't believe it makes sense even to the people who are describing it. So, but on a much easier to understand level, when we are dealing with conservation of angular momentum, there's one relatively simple condition that we can generally ensure around short periods of time, and that is we can't have any external, well, with momentum, with linear momentum, it was forces. We can't have any overall external forces on our system. With angular motion, rotational systems, we have to make sure that there is no overall torque on the system. The whole system, whatever objects are interacting, cannot be experiencing an overall torque that is changing the angular motion of that system overall. And you'll see an example of that shortly. We can have collisions, just like we could have collisions between two carts with no net force. These two carts, when I bump them off each other, are each experiencing a force, but one of them is experiencing a force in this direction, the other is experiencing an equal force in the opposite direction. The overall force on the two carts combined is 0. We can do the same thing with rotating objects. So I have to get my rotating platform. Hold tight. So if we have a rotating platform like this, and I doubt my camera is going to be able to see this. I was sort of hoping that it would, but probably won't. What do you think, camera? Should we point you down? That's going to take too much work. Okay, camera, there's a rotating platform here. Okay, so, so if I get this rotating platform spinning, and then I take an object, this is spinning too quickly by the way, I take an object and I hold the object motionless above this rotating platform and then drop it, the angular velocity of this object decreases. Why? Because its moment of inertia increased as soon as I put this heavy weight on it, especially since I put the heavy weight toward the outside. But the overall angular momentum of the system had to stay the same. My block, my heavy weight, has no angular momentum. All of the angular momentum is in this rotating platform. So as soon as I drop this block, rotate it more slowly, as soon as I drop this block, the angular momentum of the system overall stays the same. The rotational velocity of that rotating platform needs to decrease. And that's what we're looking at there is the same idea. There is torque. As soon as this block comes into contact with the rotating platform, it experiences torque in the direction of rotation. But there's no overall torque because the platform itself experiences an equal and opposite torque. It experiences equal torque in the opposite of the direction of rotation. So the weight speeds up, the platform slows down. Angular momentum in this case is conserved. And the other way that we can change angular mass or moment of inertia is by changing the location of mass by using biological systems, and we saw that earlier. So mechanical systems work just as well, but we don't have something easy that's set up where we can control the mass of an object by moving it like motorized along the radius of a rotating object. Ideally, we would have a system here where I could take this mass and pull it closer to the center of rotation and move it farther out from the center of rotation without touching it and adding any external torque. If I did that, what you would see, just like you saw with Finn, is that as the mass moves farther out, the rotational speed slows down. As the mass moves closer to the center of rotation, the rotational speed increases. There is one other thing that I want you to at least think about. We're not going to make any measurements with this because it's like way beyond the scope of what we have to do. But systems that have multiple rotating objects will also have the same angular momentum, and so you get some really weird things like this. Oh God, I don't think I can do it. I'm too old to demo this stuff myself because I get too dizzy. Because you know how like your balance is like your inner ear, and my inner ear is old and worthless, like the rest of me. So I need another volunteer. So I need one volunteer who's too scared to spin around. Who's too scared to spin? All of you. I already picked on Jack. Let's say Marie. You look too scared to spin. So come back here. You will not spin. There will be nothing about this that leaves you feeling dizzy or unsettled in any way. Hold this like this, as far away from you as you can, on opposite sides, okay? And I'm gonna spin this. Okay, now try to twist it like this. You feel that? Yeah, it's weird. Everybody should try this at some point. Okay, thank you. What we're looking at here is conservation of momentum. And because this spin has a direction, changing the direction of rotation means that we're changing some angular quantity that's associated with angular momentum. We can't do that without applying a force, because we need to add external torque to change the angular momentum of the system. There's no other way to do it. This is the principle behind like gyroscopes and stuff like that. This is also the reason why when you're riding your bike, it's not that easy to fall over, right? Like this wheel can almost balance itself. I can't do it. I need it to spin faster, and I can't get it to spin fast enough. But like I can't do it. Hang on, I need help. Somebody stand up. Come over. Spin somebody big and strong. Big and strong. It's gotta be wide. Come here. Spin this thing. Make it spin as fast as I can possibly get it to go. Faster. Okay. Let's see. All right. Yeah. So sometimes if we take it for a little walk, it helps. But yeah, I can feel it. But you guys can't see it. There we go.
Oh.
Yeah.
Whoa.
So isn't that weird? And what's going on, the faster it goes, the more obvious that is. What's going on is that it takes a net torque to change the angular momentum, which means it's not going to change unless something pushes on it. Where it gets really fun, so it's got to be Alec now, I think.
What do they do?
Well, not you.
Oh, I need to get up there.
Yeah!
No, I can't. I cannot pull. I can spin the wheel though.
No, this is. You can do this. I won't make you go back. Don't be a big baby. Come on and stand up here.
No, I'm actually like folded, bro.
Aaron, what about you? Okay, come on up. I won't make it. You'll have complete control over this. Okay, stand on the platform. Hold this in both hands, far away from you as you can. Okay, and then get this spinning. Oh my God. Okay, very slowly. Tilt it like this. Watch what happens. Keep going. Spin it.
Keep spinning.
Keep going. Now straighten it out and spin it. Turn it the other way. Okay. So what's going on again is we are witnessing. You can calm down. We are witnessing conservation of angular momentum, and if he changes the direction of this spin, there has to be a corresponding change in the angular momentum of something else. And it ends up like, there ends up being actual forces associated with this, which is why gyroscopes and bicycles work the way that they do. Okay, so there's two things that I'm gonna propose to you. One of which you don't have to do, but you're welcome to. The first thing is, if you wanna just kind of play around with some really easily calculated numbers, there's a PhET simulation that allows you to do this. And you can just go to the PhET simulation and play around with it to your heart's content. Whether or not you do this, what I really want you to do is I want you to look at the angular momentum of some real rotating object that's in this room, and how its angular velocity changes as you change its moment of inertia. So that could be, with the rotating platform, you can't use this. This is a lead weight, so you can't touch this. I shouldn't either. But you can drop a book onto the rotating platform, or you could, you could figure out some fancy pants way of like attaching a mass as this thing is spinning, attaching a mass to it. Like you drop a hook down or something. I don't know, there's all sorts of clever things. You guys can come up with something. You're brilliant. We have these concentric pulleys, and if you spin them like this, it's not that hard to like drop a little mass toward the edge, so you can change angular moment of inertia that way. There are chairs that spin. There are doors and cabinets that swing open. That isn't fully rotational, like it's not making full rotations, but it's still angular motion. And what I want you to do is essentially investigate the connection between changing an object's moment of inertia and how that changes the object's angular velocity. One tip that I have is that finding moment of inertia is challenging. If we have an object that's uniform in shape and composition, then we can plug some numbers into it. So like the plastic bars are uniform in shape, but they're not uniform in composition. So if I wanted to know the moment of inertia of these, I can't just like measure their size and put them on balance, because they're not uniformly shaped. They're not made of a uniform material. The mass is not distributed evenly. And so a lot of times when we talk about moment of inertia, people jump to, well, what's the equation? And the answer is there is no equation for moment of inertia of most things. Most things you have to find the moment of inertia experimentally. You have to do some stuff and use the data that you collect to determine an object's moment of inertia. And you'll probably have to do that today. But it's super easy to measure angular velocity. If you have an object that's spinning with minimal friction, then all you have to do is count rotations. That's why there's a piece of duct tape on this right here. We can measure angular velocity of this simply by assuming that the velocity is constant, at least over a few rotations, and time it. However many times that bar goes around is the number of rotations, and time how long it takes. Divide, and that will give you its constant velocity in rotations per second. There's 2 pi radians per rotation. So whatever you get, multiply by 2 pi, and there's your angular velocity in radians per second. So angular velocity is pretty easy to measure. Moment of inertia is a bit of a challenge. The only other thing I'll tell you about moment of inertia is that we do know how to find moment of inertia of a point mass. So like the giga rotating on a string that is relatively low mass, I can tell you the moment of inertia of this system by measuring the mass of the giga and multiplying it by the distance of the center to the center of rotation squared. That is the moment of inertia of a point mass. It's also the moment of inertia of a hoop, which is basically a bunch of point masses that are attached to each other if we rotate the hoop about its center. So finding moment of inertia of some things is easy. Finding moment of inertia of other things is challenging. Finding angular velocity for things that are spinning, at least if they're spinning at a reasonable rate of speed, is not that hard. And your job is to come up with a way to tie all this stuff together to get an object that has a changeable moment of inertia and see how changing moment of inertia affects the angular velocity. Okay,